Okay, welcome everyone to the next in our series of Ferroelectures. I'm Ron Cohen from the Carnegie Institution for Science in Washington, D.C. And today, first I want to thank the organizing committee that helps run this and choose the speakers and so forth. So Lauren Palage, Cyrus Dreyer, Anna Grunbaum, and Beth Nowadnik. And Anna and Cyrus will be joining us today as panelists. Today we're really excited to have Claudio Cazorla talk about a really exciting topic, novel piezoelectric materials for photocatalytic water splitting. And Dr. Cazorla is in Spain. He got his doctorate there in 2006. And then he spent time in London with Professor Gillen and Dario Alfe at UCL, and then worked in Spain with Max Stengel, and then was recently the last couple years in Sydney, Australia, and now he's back in Spain again. Claudio wears the same two hats that I do. He has work on high pressure properties of metals like tantalum melting curve, and a lot of interesting work on active materials. And today he's going to talk about a really exciting subject that involves both theory and experiment, looking at ferroelectrics as catalysts for splitting water into hydrogen and oxygen. And I don't want to take up too much of his time, so we're going to go to him. But first, let me just say, you can type questions anytime into the Q&A, question and answer panel, and they will be addressed after the talk. So there'll be time for discussion after the talk. So without any further ado, I am going to turn it over to Dr. Cazorla.
Okay, thanks a lot. Thanks to the organizers for giving me the opportunity to present my recent work. I'm gonna share the screen. Hopefully it's gonna work. Yes, let me know if it is not working. Yeah, so, okay, full screen mode. Yeah, so, cool. Yeah, so my work, the work I'm going to present today, it's about two recent publications I've been working in, and which is related to the use of multifunctional materials, new multifunctional materials in the context of photocatalytic water splitting, or if you want, so sunlight-driven hydrogen production, right? So I'm gonna start by the end, just acknowledging the collaborators. Basically, I've been working with Dr. Kevin Liu in China in these two articles or works I'm going to present today. And yeah, I started being interested in these topics from my time at UNSW in Australia, where I had a lot of experimental colleagues working in photocatalysis. And now, currently, I'm at the University Politécnica de Catalunya, where I got my PhD a long time ago, and where I keep working on these topics with theory, but also in collaboration with many experimentalists. Okay, so let me do a bit of motivation. So of course, I guess I don't have to convince you that we are like energy. So we use it for anything, right? Technology, refrigeration, transportation. However, it seems that the way we produce that energy is probably not the optimal one. So we need to find sustainable and environmental friendly ways of producing energy, right? Among the diverse possibilities, one of them is to use hydrogen, right, as a fuel, since combustion of hydrogen involves, you can get a lot of energy out of it, and at the same time, combustion just generates water as a side product, right? So it's highly sustainable and environmental friendly. So the commercial, so in order to adopt this hydrogen economy, so to say, so we need to have some scalable commercial methods of producing hydrogen, right? And one of them currently is electrolysis. So basically we use electricity to break down the water molecules in order to generate hydrogen, right? So then that hydrogen, of course, can be stored in tanks, can be exported, and can be used in engines or fuel cells in order to get electricity, right? However, generating hydrogen from water electrolysis, so far it hasn't proved to be energetically very efficient from an energy point of view, right? So we should look for alternative, or we may look for alternative ways of producing hydrogen, right? And one of those it's to use materials in order to directly, by using sunlight and catalyst, to get hydrogen out of water, right? So this is a very promising possibility. Many people work on these materials, right? And I'm just going to focus here on the very essential properties those materials need to fulfill in order to focus, to give some direction to the discussion, right? So basically, these materials should be able to drive the oxygen evolution reaction, in which the material is going to be able to provide holes to water molecules which are absorbed on its surface, so that it can break the water molecules into oxygen and hydrogen atoms. At the same time, it needs to provide also electrons in order for two protons to join into a hydrogen molecule, right? So these are the two reactions that one of these materials need to catalyze, need to facilitate, right? And in order to, what are the requirements for those materials to do that is, okay, so of course there are many requirements, but from a, let's say, band structure point of view, the very essential requirements are that the energy band gaps should be between 2 and 3 electron volts in order to be able to absorb sunlight radiation efficiently. And then the valence band level should be below the oxidation level H2O2, and the conduction band should be above the hydrogen reduction potential, right? So basically, these two levels need to straddle these two potential energies, right, in order to facilitate these two reactions simultaneously. Of course, we know already many photocatalytic materials. However, we don't have so to say, like a systematic and rational way of improving them, right? So for instance, we have we know this tantalum nitride material, which is pretty good in terms of energy band gap and also in terms of band alignments. However, it contains tantalum, which is quite a rare element, and it's expensive from a from a cost point of view, right? So it's not a good material then for commercial scale. On the other hand, we may find materials like zinc oxide, which are very cheap. But on the other hand, they may not have like the optimal optoelectronic or band alignments properties, right? So the motivation for these works I'm going to present for this talk is, okay, so basically, can we systematically design enhance photocatalytic materials, right, from what we already know. So typically there are two approaches that we use in order to improve and enhance the properties of materials. One is mixing, so you take two materials, each has a good property, so you want a material with sharing both good properties for them, so you mix them and you expect the final mix or hybrid material to share both good traits, right, from the parent materials. Another possibility is what I call the nanotechnology strategy, which consists in stretching the material, basically to do things on the material in order to change the bond length and the electronic overlappings in order to control and design the electronic band properties, right? The works I'm going to talk about today follow this nanotechnology strategy, right? So I'm going to forget about mixing, even though that can be also like a possibility. The two works I'm going to talk about, one of them has been published in 2020, and basically it's about the epitaxial strain of photocatalytic materials. And the second work, which is basically about piezo photocatalyst, it's probably the one that it's more meaningful or most consistent with the title of the talk, right? This is a work that currently is under review, right? Okay, so I just have given you the motivation and the very basic essentials for water splitting. So I'm going to be very brief on the computational methods. Okay, so I'm a computational material scientist. So the work I'm going to show in what follows, it has been based on density functional theory calculations. So density functional DFT, it's a first principles methods in the sense that it can solve the Schrodinger equation for materials, right, without making assumptions, ideally among the electrons and ions, right? That's what is called first principles, a first principles method. In contrast to other first principles methods, in DFT, the fundamental variable is the electronic density, right? So in DFT, we don't attempt to look for the wave function of the n interacting particles that form our system, right? So this difference allows DFT for a certain accuracy in the calculations, while at the same time it allows for a lot of feasibility, right? So with DFT we are able to do many types of calculations in a very efficient way that otherwise we couldn't do, or we couldn't do easily with other first principle approaches, like for instance quantum Monte Carlo, that on one hand they can be probably they are more accurate than DFT, but they cannot allow for feasibility in practice, right? So DFT, okay, so I'm not gonna go into details, but DFT also what it does is to exploit mapping between the many-body interacting system to a system of non-interacting particles through the construction of the Conshan Hamiltonian, right, which looks like this. So here we have kinetic energy term, an exponential, an external potential, and then the Hartree term, so Coulombic interaction, right? And then here on this exchange correlation term, we have everything that makes our system of electrons and ions quantum, right? So here it's all the quantumness of the system concentrated. And it's very important because it's basically what it's a part that acts on the gluing of the atoms, and which allows us to access actually in a feasible way the electronic band structure properties of materials, right? In principle, DFT is it's an exact theory, but in practice it is not, because we don't know this exchange correlation functional, how it looks like. So we have to do assumptions and approximations on that term here, right? That's the only fundamental origin of uncertainty, even though this is not under control, it's not under control, right? So depending on the material you're looking at, these approximations can be quite problematic. In our case, okay, we're going to assume this is not going to be the case. So for the systems we're going to talk about, DFT is pretty nice, pretty good. And the type of calculations that are behind the results I'm going to present consists in band alignments calculations, in which you basically have to deal with the slab systems as well as bulk calculations. Then, because I'm gonna explain results for thin films, I'm also going to resort to what is called bullet strain relaxation. So surface effects are disregarded, but we consider the effect of having some strain on the system, right? Also, one of the two works I'm going to present, it entails some high throughput screening of materials, which is a kind of like a systematic and way of looking for new materials. And also, in addition, okay, so following calculations, right? Okay, I'm not gonna go more into the calculations. I'm just gonna focus now into the results, the physics of the results, right? And I'm going to very briefly go into the first work, which is not specifically on piezoelectrics, but which motivated the second work, which is entirely on piezo-photocatalytic materials, right? Okay, so in material scientists have explored quite systematically what is called epitaxial strain in order to improve or change the functional properties of materials. So this epitaxial strain strategy consists basically in growing a thin film of a material on top of a substrate, right? For which there is a lattice parameter mismatch, right? And depending on how that lattice parameter mismatch between the thin film and the substrate it is possible to introduce either a tensile strain or a compressive strain on the material, right? That the strain, of course, acts on the plane of the interface between the two materials, the substrate and the thin film, right? So this first work, what tried to answer is, okay, so what about using this kind of strategies for improving the photocatalytic activity of known simple oxide materials, right? Which are the typical materials that one finds in this context of photocatalysis. Okay, so we did that. So we look into xerium dioxide, which is one of the most known catalyst materials, right? Or most extensively studied, right? And what we did was to look into how the structural and electronic properties of this material changed under these epitaxial strain conditions, right? So we explored both tensile, just represented by positive epitaxial strain in percentage, right? As well as compressive when these numbers are negative, right? So we found that, in fact, so here in this plot, so I just represent the energy band gap, which is on this axis here, how it changes with epitaxial strain. And then on this other y-axis, we have how these band alignments, right? So this is the top of the valence bands, and this is the bottom of the conduction band. How do they change as a function of epitaxial strain, right? Where here we have the HER and OER potential energies, right? So, okay, so for the energy band gap, in fact, there is a strong effect, right, as induced by epitaxial strain. Later on, I will explain very briefly what are the fundamental causes of this, right? But also, but this is something that, okay, so had been done before, right, was known. But what we were looking at was how these band alignments were changing at the same time, right? So we found out that, in fact, whether at zero strain, so if you don't do any epitaxial strain on the material, you have a material that it has a too large energy band gap, 3.2 electron volts, in order to use it for direct photocatalytic applications, right? And also the straddling of the two energy levels of interest for water splitting was not too good, right? So this point here was too below the OER energy level, right? However, as you increase this tensile stress, right, or strain on this material, right, you come to a region from 2% on, right, in which your band alignment, your band gap, it's reduced down to 3 electron volts, which is good for absorption of the sunlight, right? And at the same time, the band alignments tend to be positioned in a more optimal value, right, in order to drive this water splitting reaction. We did the same for another archetypal photocatalyst, as it is titanium dioxide, which was actually the first photocatalyst that was reported for water splitting reaction, right, long time ago. And in that case, so we did the same kind of calculations, and we found out some similar or quite similar tendency trend on the energy band gap, right? So essentially, as you compress you increase the compressive strain, the band gap increases, whereas when you go on the tensile strain side, the band gap is reduced, right? At some point, it's reduced down to below 3 electron volts, which means that you have just changed the properties, the absorption, light absorption properties in a way so that, you know, this material can be more efficient. And on the other hand, the band alignments here, if at 0 strain, they were not optimal because basically they were not straddling the energy levels of interest. Here I just changed, so this is very close to the HER level, but okay, so here is just, we just put another reaction, but okay, just imagine it's very close to the OER, right? However, the band alignments, how they move, how they change under the epitaxial strain were not too optimal for water splitting, right? Since on the side where the band gap is somehow improved, right, the band alignments still are not good enough, right? So this point here should be a bit higher, and this point here should be a bit lower, closer to this line over here, right? So we report many more things on this paper, right? But essentially we worry about, okay, so what happens? So can we just predict these changes on the energy band gap in a systematic way? So we can really say whether this epitaxial strain can be useful or not for this band engineering, right? Band structure engineering, right? The reason, okay, so when it comes to energy band gap, it seems that we already know many things about how epitaxial strain can affect it. So in fact, many of these effects can be, so these strains, both for the cerium dioxide and titanium dioxide, they basically can be understood in terms of symmetry breaking of the structure, right? That gives to some band structure degeneracy lifting, right? So essentially at 0 strain, some of the energy bands are degenerated at the top of the valence band and bottom of the conduction band. But when you introduce this strain, the symmetry it's lower, and as a result, the degeneracy is broken, right? It's lifted. And as a result of that, you can get like a smaller energy band gap, right? This was, for instance, already shown by some people in strontium titanate, right, which is a more complex probably material than the two that I've shown, right? But essentially, okay, so they shown this effect about the how the symmetry breaking was important in understanding these effects, right? Of course, that's not, in our case, was not the only effects to take into consideration. So on the compressive side, also we had to resort to some screening, the electric screening arguments in order to understand why this was increasing up to here, right? But pretty much, I mean, these symmetry arguments can be very useful to understand the evolution of the band gap, right? However, when it comes to the band alignments, we realized that there was not or at least we didn't know at the time, any systematic or any effect that could give us a systematic trend on the band alignments. So for instance, here, two materials that for which the band gap evolved in a very similar way, then you look at the band alignments and actually the evolution are pretty much opposite, right? So here, for instance, the band alignments tend to go higher in energy as you move from the compressive to the tensile strain side, whereas in titanium dioxide, it's the opposite, right? So you go from higher to lower, right? So to the question, can we predict, understand the changes induced by epitaxial strain on band alignments? So at that time, answer would be, honest answer would be no idea, right? Okay, but that first work motivated us to do the work that is currently under the review and that you can check on the archive under this code here, right? Which I'm going to explain now, and which is probably the most interesting part of my talk, right? Okay, so just as I said before, so this is the ideal situation one wants for an ideal photocatalyst. So you want these two energy levels to straddle these reaction potential energies, right? So that you can just introduce electrons and holes into the water molecule and to form these hydrogen molecules, right? However, this is never the case, or most of the times you don't have this situation, but you have something like this, right? So even if your band gap, it's optimally for absorption purposes, in the sense that it's below 3 electron volts, right? Typically, the band alignments, you know, it may be not good at straddling these two energy levels, right? Okay, but we realized that there is a by our work in other materials in the field of oxide perovskites, we realized that there are a family of materials called piezoelectric materials that they have some very interesting properties when it comes to possible photocatalyst applications, which is the following one, right? So piezoelectric materials, when you apply an electric field on them, you get a strain effect out of it, right? Or conversely, when you apply a strain on the material, you get an internal electric field inside of it, right? So that internal electric field can be very useful in the context of photocatalysis for many reasons. The first reason is that that internal electric field then can bend the band, right? So they can change the band alignments in a kind of systematic and quantitative way, right? So it just introduces this constant slope, which basically has to do with the intensity of the internal electric field, right? So this is good because at some point you may think that, you know, at some point, some regions of your photocatalyst, because of this band bending, you may end up having an optimal position of your band alignments, right? Which is something like this, right? So we start from here. So now we apply some strain, either by introducing some ultrasounds on it, or by doing some mechanical actuation on the material. And out of that, you just bend the band alignments, and at some point you may get the optimal situation for what it refers to band alignments, right? So this is the first possible benefit of using piezoelectric materials in this context of photocatalyst. And the second one is that, of course, also this internal electric field, what it makes is to enhance the recombination time of the excitons that you form when the material absorbs these light photons, right? So essentially, a photon comes here, so you create this whole electron-hole pair, right? Typically, this electron, this excites after some short time, so you don't get any more this separation of charges, right? This is not good. So you would like to have these two charges separated as long as possible in order to be able to drive these two reactions as efficiently as possible. However, you know, when you have an internal electric field, you create now these two charges, and because of the electric field, they just are accelerated into opposite directions, so that somehow you are depleting the recombination rate of these excitons, right? So this is something also that it can be very beneficial, right? This internal electric field can be used for avoiding a fast recombination of electrons and holes. Okay, so on the other hand, piezoelectric materials are quite abundant in practice, because the only requirement they need to fulfill from a symmetry point of view is that they are not centrosymmetric, right? So piezoelectric materials englobe also ferroelectric materials, right? The thing is that piezoelectric materials is even corresponds to a larger number of materials, right? So you don't need to have like a switching ferroelectric switching, right? So this is also a very good trade. So there are a big number of piezoelectric materials out of there, right? So abundance, internal electric field in order to bend the band alignments and to avoid recombination of electron and hole pairs, right? So this looks like very interesting properties, but as a matter of fact, I mean, piezo-photocatalytic materials, right, has been very, very scarcely explored in the field of catalysis, right? So basically, the archetypal piezo-photocatalytic materials, so those that has been reported in the literature, that has been studied, right, are zinc oxide and barium titanate, of course. Barium titanate is an archetypal piezoelectric material, and oxide perovskite that is very well known, and it's very stable, etc. It's very cheap, right? So it's a very nice material for all these applications. However, what we the aim of this work was, okay, so can we predict, can we select all the new piezo-photocatalytic materials, and can we somehow, for that selection, come up with a simple electrostatic model that may help us in understanding the functioning and the properties of these piezo-photocatalytic materials, right? So that was the motivation of the work I'm going to present now. Okay. So to start with, okay, so we made a very, very simple, super simple electrostatic modeling of piezo-photocatalyst based on a piezoelectric plate capacitor model, right? So we have here a plate capacitor, right? And here we have a dielectric material. So let's imagine that this material is not just dielectric, but it's also piezoelectric. And let's imagine that it doesn't have like a spontaneous polarization, right? So if you don't squeeze it, if you don't put ultrasounds, the polarization is 0, right? So basically, you have that the potential drop between these two plates is 0, right? Because as everyone knows, that potential drop is equal to this relation here, where C is the distance between the plates, epsilon is the electric constant, and D is the electric displacement, which is basically equal to the charge surface density, right, on the plates, okay? But now let's imagine that we take this piezoelectric plate capacitor and we just, act with some ultrasound or some actuator on it, right, on this direction. So as a result of this ultrasound or actuation, mechanical actuation, we get some charges on the plates, and now we will have, of course, some different non-zero potential drop between these two plates, right? That will be equal basically to the charge accumulation, the density of charge accumulated on these two surfaces here, right? Divided by the electric constant, okay? So, okay, so I didn't want to do that. Yeah, so basically, okay, so this piezoelectric material here, it's, as I said before, it's characterized by the electric constant, but also by this piezoelectric coefficient. So to make things ultra simple, we are just assuming that, this is a isotropic piezoelectric material. So we just don't care about any direction perpendicular to this one, the one that is perpendicular to the two plates. So in this case, we can easily find out an expression for the module of the internal electric field, right? So we have that this internal electric field is equal to the potential drop divided by the distance here, right? If we now assume that we have a linear, we assume a linear approximation for this potential, right, that appears as a function of strain, right? Then we have, based on this definition of this piezoelectric coefficient, that this internal electric field is proportional to this piezoelectric coefficient here, right? So at the same time, we can, just based on this expression here, we can define this new piezoelectric coefficient, in which just simply tell us how this potential drop changes as a function of this uniaxial strain, right, applied on this direction, right? And it gets something as simple as that, right? Again, it's a huge simplification, but we do this just because then we are going to use this simple model in order to make a high throughput screening of materials, right? So based on this simple equation here, we can consider that the band bending, right, or the maximum band bending over a unit cell for a given material like this, right, would be equal to this alpha eta parameter that is defined here, equal to basically the piezoelectric coefficient E33 divided by the electric constant, right, multiplied by the strain that we applied, also considering, again, a linear approximation, right? So in other words, in terms of band alignment tunability as induced by a strain, we can say that good piezophotocatalytic materials should exhibit large alpha eta parameters, right? Because then we will have large band bendings, we will have large internal electric fields created in the interior, right? And therefore, we will be able to, just by applying very small strains, sorry, not epitaxial, just strains, right? To get some optimal band positionings, right? On the other hand, materials with a very small alpha eta parameter value will be very bad in terms of possible band alignment tunability, okay? So again, of course, this is super approximated. It's not exact. So we are disregarding surface effects. We are disregarding anisotropy effects. We are disregarding also, for instance, the effect on the band gap as a result of the uniaxial strain, etc. Right? But on the other hand, this simple modeling allows us to go on doing a high throughput DFT screening, right? So this is what we did. So basically, we went to the materials project database, where there is a dedicated piezoelectric subdata set of about 1,000 materials, right? And we, by using some public tools, right, some freely available tools, we perform some high throughput reads, right? So basically, we sift those materials, those piezoelectric materials that exhibited alpha eta coefficient larger than 1 volt, right? Again, the larger the value of this parameter in our modeling, the better the material in terms of band alignment tunability. But of course, because it's not just about moving around the band alignments, it's also about the energy band gap. From the materials that fulfill this first condition, we finally selected those that also had optimal energy band gap traits, right? So basically, a band gap in between 1.2 and 3 electron volts. So we did that for over 1,000 materials, and from all those, we found out a total of just around 40 materials that fulfill this first condition, and from those 40 materials, about 20 only fulfill this second condition, right? So those 20 are those shown here that now I will show in a table, right? So these materials here that entail some halides, oxides, chalcogenide, nitrides, and other semiconductor materials, right? In principle, according to our high throughput screening conditions, are optimal for these piezophotocatalytic applications, right? So here are those around 21 materials, right, that we sieved. Okay, so we found barium titanate among the best performance. Of course, this is a good thing. That is saying that our screening probably is fine, right? Because this material is known to be a good piece of photocatalytic material, right? On the other hand, zinc oxide, which is the other archetypal for the piece of photocatalytic materials, didn't appear out in our screening just because the band gap that it's appearing on the materials project, it's just below 1.2 electron volts, right? I will come back to this point later on. But just to mention that, okay, so our screening was quite successful in finding new materials and simple ones, all of them, of course, piezoelectric. So here is the space group, right? and all the properties. So we have all these are non-polar materials. We have the electric properties. We have the piezoelectric coefficient, the band gap, etc. And finally, the value of this alpha eta, right? Of course, for having a large alpha eta value, you need to have a combination of two properties that is not common, right? So you need to have a high E33 piezoelectric coefficient, and at the same time, you will ideally need to have a small dielectric constant, right? Because this dielectric constant goes into the denominator of this descriptor here, right? However, that's not typically the case, because materials that has a large piezoelectric coefficient also have, of course, a large dielectric constant, right? So maybe that's why there are many materials that has been just overlooked, right, on this for this potential piezo photocatalytic application, right? So, for instance, we found out one material that hasn't been considered so far for these applications, or in this context, which is lanthanum nitride, right? Which is it's a quite large. It presents a quite large alpha value, right? Also some halogens, right, containing platinum, probably not too optimal in terms of cost, and also some quite weird, you know, maybe not obvious materials that has not been considered even in the context of catalysis, right, or photocatalysis. I'm not just saying piezo photocatalysis, I'm just saying photocatalysis, right? So for instance, this material, it's known from its topological insulator properties, but according to our search, it could be also good, potentially good for these piezo photocatalytic properties, right, or applications. On the other hand, also we found out some other materials, simple ones, which are very cheap, very well known, and which hasn't been either considered on this context, right? But according to our CIF, it could be a promising one. Okay, however, one has to be cautious because, of course, all the data in the materials project database relies on standard approaches, right? That we know that particularly are not good for these energy band gap and band alignments properties that we are interested in, right? So for that reason, what we did was to refine the data found in the materials project, right? So of all those 40 something material compounds that we first sieved from the materials project database, we recalculated the energy band gap and the value of the alpha piezo photocatalytic parameter that we define, right, with a much stringent conditions, all right, by using hybrid functionals, right, and by using quite large energy cutoffs and K-point grids, right. By doing that, we find out finally, okay, so we come out with our final list of candidates, right, materials, right, which are these 16 materials here, right, among which we can find some that are not really suitable for water splitting, because, for instance, unfortunately, the first material appearing in our list, so this list, it's just ordered according to the value of the alpha descriptor, right? So the one with the largest descriptor value, right, it's this potassium iodate, right? However, so it has a very good energy band gap and a huge piezo photocatalytic parameter value, right? However, it's water soluble, right? So that's for sure not useful for driving any water splitting, because before doing that, it will just be destroyed in the water in aqueous environment, right? So the same happens for some other similar materials like this one here, or this other one here, which anyway were not known in this context of catalysis, right? However, we find out some nice results. For instance, we found out this potassium niobate, right? Which is it's on second, but efficiently it's on the first position, right? Because it's not water soluble, right? Which is it's pretty much ideal from a cost, from a band gap, from a band tunability point of view, right? So it's the one that goes on top of our list, and in fact, we just found that some very recent reports in the literature has found that this material it's experimental reports, it's a good piece of photocatalytic material, right? So a good thing that our search just find out this material, but it's not totally new, so to say. On the other hand, we also identify these simple oxides, nitrides, like lanthanum nitride and gallium nitride, right? Which are also quite suitable in terms of band alignments tunability, right? They're also quite simple in terms of the structure, etc. And their band gap seems to be pretty good. Gallium nitride probably is too large, but the lanthanum nitride, which is probably not as much known as gallium nitride because this is very well known in the context of LEDs, right? But this one, it's not so well known, but according to our calculations, it seems to be more suitable for this piezo photocatalytic application, right? Then also these halides, so platinum fluoride, right? It's quite good in terms of band alignment tunability, but probably it's not ideal in terms of cost. On the other hand, okay, so we also, our final screening identified barium titanate and zinc oxide, which are the two archetypal piezo photocatalytic materials. So this is a good thing. And actually they are quite well positioned in this list, right? Interesting other materials that we also found because were not considered before or hasn't been considered yet in experiments, right? Is this cadmium sulfide and this other scandium copper sulfide material, right? Which are known from different contexts. Again, this is known from also the optoelectronic properties, but according to our calculations, if you put this material under ultrasounds or under mechanical actuation, it may be also quite good piece of photocatalytic material. Then there is this other weight material known in the context of topological insulators, but not in the context of catalysts or photocatalysts, right? Which seems to be also pretty promising, right? Etc., right? So there is this long list. So in the final positions, we have silver iodide and carbon silicon carbide, right? Which are very well-known materials and which, you know, they have quite optimal properties. Also, they are very cheap. So these probably two guys are pretty good candidates for doing for scalability purposes, right? Okay, so that was the results for our high throughput screen just based on the value of this alpha descriptor. Of course, that's not enough. Once you do this high throughput screen, you need to do some validation. So that's what we did. So basically we went to validate with DFT techniques our screening. So we choose few of these materials. I'm gonna go a bit quick on this because I only have 3 minutes left, right? So essentially, we had that, you know, we look at the energy effect of uniaxial strain on the band gap and also on the band alignments. And at the same time, we check out the band structure properties and the vibrational stability properties, right? So here in both sides zinc oxide, we have some monotonous tendency of the energy band gap under increasing uniaxial strain. So we can understand this decrease here in terms of band splitting, band degeneracy split lifting as induced by symmetry breaking, right? On the other hand, this increase of band gap here, it's more related to the value of the crystal field, right? So here there is no any significant band splitting or band degeneracy lifting effect, right? So that this increasing here, it's not due to symmetry breaking. It has to do with more electrostatic effects. Anyway, so we already kind of knew this thing here. We check that the vibrational properties were fully maintained, right? And this is where, you know, so we specifically calculated the band alignment. So the top of the valence band, the bottom of the conduction band, under these string conditions, right? And we find out that in fact, you know, these lines here, they look pretty linear, right? Which is kind of like consistent with our model, right? Our simple plate capacitor, piezoelectric plate capacitor model, right? And in fact, the numerical value that we get for this slope here, it's something compatible with what we got from our alpha value, right? we did the same for silicon carbide. Silicon carbide is very interesting because it has many different polymers. Some of them are piezoelectric, some other are not piezoelectric. So we can very, compare very meaningfully how the band alignments evolve under unixel strain. So do not forget that our main motivation for this work was just to see whether we could have materials in which the evolution of the band alignments could be somehow systematically and rationally predicted, right? We found out that in this case also the modeling we did was kind of like meaningful, right? And compatible with our explicit DFT calculations for the band alignments. Here, the evolution of the band gap can be fully understood in terms of symmetry breaking arguments, right? This is a 4H polymorph, which is piezoelectric. The same material has another polymorph, which is cubic, and therefore is not piezoelectric. And in fact, we did the same calculation just for cross-checking, right? And we found out that in this case, certainly the band alignments were not showing any kind of like linear or systematic tendency, in contrast to what we found for the same material in its piezoelectric polymorph, right? So we conclude that even though, of course, the plate capacitor model is very approximate and it neglects many important points, it can be used actually for, or it's meaningful to be used for these kind of screening strategies. Okay, I'm just gonna go to the conclusions because I see my time is finishing. Just to say that there are other, of course, there are other descriptors or other properties that are also necessary to check in order to find out whether the materials are good or potentially good photocatalysts or not, right? It's not just about the band alignments and the energy band gap, but in any case, we just focus on those two properties, right? So the conclusions out of these two works is that, in fact, nanotechnology strategies based on strain engineering or uniaxial engineering, biaxial engineering can be used for achieving rational design of photocatalytic materials. The energy band gap of some of those materials can be understood in terms of well-known symmetry breaking of the electric arguments. And out of our work on piezoelectric materials, we can we have shown that piezoelectric materials can really offer a rational way to adjust band alignments in a controlled manner, right? So this is something that you may not find in other families of materials, right? So this is a very important conclusion out of our work, and we have shown that, you know, many new, so overlooked piezophotocatalytic materials could be checked in practice, could be validated in experiments, since according to our calculations, they are very propitious in terms of band alignment tunability. It's all. Thanks for your attention. I'm open to any questions you may have. Yeah.
Okay, great. Thank you very much. There's something funny about Zoom today. I don't know if anybody else has a Q&A panel, but for some reason, maybe it's from some upgrade in Zoom, and we don't seem to have the Q&A panel. So instead, people should type their questions into the chat box. I hope people have a chat box, and you can also raise your hand, and I will see that for sure. So we'll start with some questions from our panelists. Cyrus, would you like to ask something first?
Yeah, sure. One question I had was, there are a few of the materials you kicked out because they were water soluble. I was just wondering how you determined their solubility in water, if that was the experimental fact or if it was from calculations. I think you're muted.
Yeah. Of course, yeah. Experimental fact. So once we had this list of materials, we just went into the literature. So this, you just go to the guys who deliver these materials to people doing experiments, and you get this list of properties, and then you can see whether it's water soluble or water reacting. Also, there were a few of them water reacting. So that's something when we do simulations, we don't care about. But then if we wanted to experimentalists to use it, then it's important information, right? So yeah, just based on what we found in the literature, yeah.
Got it. And one more quick question. Are there challenges is calculating the absolute band alignments for polar materials? Because it seems like it would depend sensitively on the surface you choose to do the calculation and things like that.
Well, of course, depending on the composition and the structure, etc., of the material, you may have different terminations, right? For the simplest one, for the binary, it's much simpler than that. But for instance, when you have 3, or depending on the structure, then you may have different terminations. We check out, of course, there are many calculations behind these results. We check out, in those cases, we check out the different terminations, and we took the promising one, right? So we just look at the termination that could be more promising, right? So, but in fact, this when it comes to the band alignments calculations, that's kind of subtle details one have to be careful with. Thank you.
Anna, do you have a question?
Thank you very much for the great talk. I also have a question on the screening, because you mentioned first you look for the standard DFT and said, the band gap is wrong, so we do it again for some chosen materials. But how could you bring in then the tin oxide? So how do you choose the additional materials to test, not in your list before? Someone missed that point.
So probably I was not clear enough. So basically, the first condition was materials showing alpha value larger than 1 volt, right? So, and then our first sieving was taken as a second condition, those with band gap between 1.2 and 3 electron volts according to materials project, right? But again, we know that materials project is not totally accurate, of course. So what we did was to just recalculate for all these 40. So when you do this with the raw materials project data, you get out with around 20 materials, right? But some of those, of course, then when we recalculate it, right? So we have, because we are doing materials project, so we have access to the structures. So we just redo calculations with a much refined approach. So we recalculate the energy band gap and the alpha value, right, with the piezoelectric coefficient and the electric constants. So then out of those 40 something, right, we end up with 16, right? So in other words, from the initially 20 materials that were picked up, some of them, after this refinement, they were discarded because, in fact, their energy band gap was too large, right? And also from those materials that were initially discarded because the energy band gap was too low, they were then picked up on the refinement. For instance, zinc oxide. Zinc oxide in the first screening was not popping out because it has 0.7 in material spray, right? Because it's GPA, right? But then you do it with hybrids, and then you get something that's 1 point something, right? So it reappears on the final list. So conclusion is that our conclusion at least is that when you do this kind of screenings, of course, you need to be very careful with just getting the data straight away from materials project and just using it like that, right? Of course, I mean, materials project it's essential for this kind of investigations, right? And of course, the data there it's got with standard functions, of course. But once you get some screen materials, it's good that you just make sure by doing some refinement of them, especially if you are interested in these optoelectronic techniques, of course.
Yeah, okay. Thank you.
Great. So we have a couple questions that people have typed in. So a question from Sobit Singh is, how reliable are HSE predictions compared to GW in this case? And then he says, I suppose that band alignment may substantially change for GW and perhaps change the whole analysis.
Well, okay. So of course, hybrids are not the gold standard in terms of these energy band gap and band alignments. GW, of course, it's much more accurate and will provide you probably some different results, right? However, of course, because we are doing a high throughput study, right? So it's at some point you have to have some balance between feasibility and accuracy, right? And we thought that we achieve it with HC6, right? 006, right? Of course, now it would be a good thing to just go on using GW to pick up maybe the 2 or 3 top ones, right? Materials that we have selected and do the analysis even more accurate. That's for sure. That's a good thing to do. But I just can say that we cannot just forget that this is a high throughput screening. And in fact, I do agree that with GW, of course, some numbers will change, right? On the other hand, probably they will not change that much, or not to say that one of the materials that we have picked up that we believe is good is going to turn out to be totally bad, right? I would say that's not going to happen, but of course it could be that some of them that are on the boundaries of the energy band gap, or acceptability, it could be that they were finally discarded, or maybe some other were pick up. Yeah.
We have another question from Joe Briscoe. Is the shift in band positions related just to the strain, or is it also related to a voltage developed with the strain?
Well, of course. Okay, so so in our simple model, electrostatic model, we just have assumed, in other words, our screening has been based on the simple assumption that the band alignments change with uniaxial strain was only due to electrostatic causes, so to the internal electric field that develops in the material. However, that's not the case, of course, because we have some dipoles, surface dipoles, for instance, that they will change also as you have some strain applied to the materials because they are piezoelectric. You will have changes in the band gap, for instance, that we haven't considered. But then that's why we have done our validation for zinc oxide and for silicon carbide at the end. The final slides are shown, right? In there is no any assumption. There is just the DFT calculations, right? So in that case, you have all effects. You have the electrostatic effects, or in other words, the effects from from the electric field that develops in the interior of the materials, but also then you have all the surface effects that we take into account by doing these slab simulations, etc. Right? Also the anisotropy of the material, anisotropic piezoelectric properties, etc. Right? So the simple model only disregard all these other effects, only takes into account the electrostatic, but in reality, of course, the other effects can be also important. Right?
Thank you so much for a great talk and great discussion. I even have more questions, but I'm afraid we're out of time. And I just want to make a few last announcements before we go. Thank you so much, Dr. Cazorla. That was great. And hopefully people will be thinking about this. Let me just show if I get the right screen here. I just want to mention we meet again next month, September 8th, with Professor Takahashi from University of Tokyo, who's going to talk about terahertz optical effects in ferroelectrics and multiferroics. And I want to mention also to please keep your calendar free for the workshop in February 5th through 8th, 2023 at the Colorado School of Mines in Golden. And we have an organizing committee together, and we're putting together details, and you should get the formal announcement of the meeting probably in early September. And thank you all, and we'll see you next month, and we'll say goodbye now. Thank you. Bye-bye.
Thanks.